Welcome, everybody. Um, Good morning to some of you, good afternoon, and good evening to others of you. We want to welcome you to Maverick's 6th webinar, and actually the first one here of 2021. If you're a returning attendee, we thank you for your continued interest. It means we haven't bored you to tears yet, so we're happy about that. We hope to not ruin that with this one. If you're new, we appreciate your attendance. We hope you find this beneficial. We're going to talk here today about causes of FRP nozzle failures and how to prevent them. So here we go. Just a little bit about me. My name is Darryl Mikulec. I joined Maverick in 2006 and now am Maverick's engineering manager for the past few years. Maverick Applied Science, if you don't know us, it's a engineering and inspection company. We specialize in FRP composites, other non-metallic materials like thermoplastics. We have a pipe support division. We have a catalog of custom pipe support specifically and custom designed for non-metallics, FRP, thermoplastic, those types of materials. The other thing we do is we act as owners' liaisons for engineering and construction assistance. So that can include anything from bid reviews, calculation reviews, drawing reviews. We do quality assurance, quality control inspections. We make sure project specifications are met and industry codes and standards that are specified are satisfied. I'm an active member of ASME RTP1 Design Subcommittee, and I'm currently the vice chair. Soon to be chair, I think. I hear the chair is retiring. He may be listening in. He's laughing right now. So soon to be chair of the NPPS NM2 design subgroup for FRP pressure piping. For those not familiar with this, this is a slide just showing how to ask questions. We highly encourage questions. My goal is to talk for about 40 to 45 minutes, leaving 15 minutes or so for questions. So feel free to ask any and all questions. We'll gather everybody's questions, combine similar ones so we can get to as many questions as possible. I have slide numbers on each of the slides at the bottom right, so it might help you be more specific with the slide that brought up the question. If we don't get to it live, there could be a reason for it. Maybe there are too many questions, or maybe it's a little bit more nuanced, but we'll be reaching out by phone or email to answer any unanswered questions. General outline of what we'll be talking about. I'll introduce the problem itself, a little bit of background on nozzle issues. I want to spend some time talking about FRP nozzle installation, what makes it unique that may lead to some of these issues. We'll talk about causes of nozzle failures, how to prevent them. I'm sure everybody's interested in that. I'll give a few methods for strengthening the attachment. How can we do that? Then we'll discuss what allowable nozzle loads are, or what they could be, or what they're not. We'll finally discuss nozzle stiffness, which definitely plays into that as well, before finishing with some final thoughts. So keep these expectations in mind as you ask your questions. In my mind, if you can identify these following items, I'm satisfied with the presentation. So the viewer should be able to understand what makes FRP nozzles susceptible to failure. The next expectation would be to identify ways to avoid nozzle failures. They should be able to define basic methods for strengthening nozzles without the need for analysis. Understand why generic allowable loads are so difficult to provide. And finally, have a better understanding of how nozzle stiffness assumptions affect the calculated nozzle loads. So there are some technical aspects, but it's not going to answer every single question. There's no silver bullet of this is exactly how you calculate the allowable loads for any and all situations. So it's more to educate, more to provide an understanding, so you understand the problem, understand the issues, so we can avoid those in the future. So some background. Quite frankly, there are too many nozzle failures in FRP construction, but why is that? So ASME RTP1, which is in North America and even worldwide, but especially North America, is the preeminent FRP tank design standard. In RTP1, it requires the consideration of loads imposed by piping as part of the sustained loading evaluation, which is great in theory, but I'll tell you it's poorly practiced in reality. Rarely are the tank and connected piping provided by the same manufacturer. Tank designers usually end their scope at the flange face, of the nozzle, pipe designers generally consider the tank flange the end of theirs. So what about the in-between? Communication is often poor, responsibilities are unclear, who's in charge of what. So what does a lot of people do? Expansion joints solve the in-between, right? Well, not necessarily, and we'll discuss a little bit about that. I think first we need to clearly describe how nozzles are installed. Some of you are more familiar than others, but for those not familiar with FRP as much, or even just manufacturing, you may have this picture in mind that FRP nozzles should be like steel nozzles, where there's no gap and the weld is at the opening, sealing any kind of gap there. FRP will almost always have a gap, and depending on the fabricator, the hole may not be tight fitting or smoothly cut. You can see on the picture on the right, it's a little jagged. Somebody just took a Sawzall on that and hacked it up pretty good. Well, RTP1 does have tolerances on the hole size, but it's certainly not 0 inches. So we have the flange installed in an oversized hole connected by an overlay. So think of an overlay more or less like a piece of tape on the outside. The gap is filled with putty, maybe a little bit reinforced, but it's really only to look nice and create a transition radius so you can smoothly apply that overlay. You need something to roll out against, so they put that putty in there to seal it up. The gap itself is probably the largest contributor to nozzle overlay delaminations and ultimate leaks or failures. And this is what we're trying to address with this presentation. Okay, so what loadings are we worried about? What are the significant loads on FRP nozzles? Primarily, you have the radial load. It's an outward load, can be from internal pressure, attached piping, or it could be from bolt torque. So let's go through the mechanics. How is this reacted by the flange and then the nozzle itself? So you have the bending moment on the flange from that outward load because it's transferred through the bolts, which causes a high stress in the hub region. So surely many of you viewers have experienced this, and we'll show some examples of where this max stress has been realized. Assuming that's okay, then the load is transferred through the overlay attachment on the nozzle itself. The overlay thickness and the length needs to be sized for the load, but it's usually not a problem, but I will show a couple instances where this actually is a problem. Finally, the load is reacted at the bond line connecting to the vessel. So the bigger the gap or radius, the more flexible the overlay becomes, which can lead to peel. Now, if you don't know this, know that FRP is very weak in peel. As a frame of reference, 24-inch manway exposed to 8.5 psi of pressure. So that's internal, or it could just be hydrostatic pressure, just fluid weight. So it's a tall tank, 20-foot tank that has a lot of hydrostatic pressure. If it's 8.5 psi or more, technically the manway will not pass RTP1's peel check of being less than 50 pounds per inch. So that would tell you it's going to peel for manways exposed to relatively low pressure. One of the causes of nozzle failures is due to short bond. I said it wasn't always, but there certainly were instances of this. So in this case, a manway blind blew off. It's a pressure vessel, someone was hurt. So this is why some manufacturers have such heartburn about projections being too short. If you look at just theory, bond length doesn't have to be very long. And I'm saying something like an inch bond theoretically may be enough to resist bond shear, although many standards say it's really 3 inches minimum. So you'd think you have a lot of safety there, but that's theory. It's extremely difficult to do good work when you have such short projections. If they can't access this area easily to roll out the material to get a good bond, the bond quality will suffer. Another cause of nozzle failures is from poor material selection, poor specifications, and poor engineering, honestly. So this isn't a tank, this is a pipe, but it's a nozzle all the same. In this case, the connection was just purely adhesive joint. Adhesive joints and bending are prone to bond line failures. The bond strength and pure tension, if you're just pulling on it, is much different than if you're bending this piece of pipe, and that's what happened here. This type of connection needed more attention during the engineering phase. That could have meant an overwrap if there were elevated stresses on this nozzle. It could have meant moving a support around to increase the flexibility and reduce the stress in this region. So poor material selection and engineering led to a failure like this. One of the primary causes of flange failures is over torque. We see and hear this over time and time again, but it's a problem that unfortunately hasn't gone away. So what is actually happening to the flange under that high radial load or excessive torque. On the image on the left, you can see it's subtle, but you can see that the flange is actually bending inwards, the flange face is. The animation here, hopefully you can see it pretty well, shows where that max stress is, where that red point is right in that hub transition, which is honestly what we would expect. Cardinal rule for FRP that you hear a lot is do not bolt full face, flat face FRP flanges to raised face valves or flanges. You're told to either use filler rings or just use lap joint FRP flanges. So the left picture is a prime candidate for hub cracks because of excessive torque. It's just going to bend that flange face inwards like we just saw, which, spoiler alert, it did. I didn't want to show that picture because this was a little bit more impactful, but you can see where that crack is, and remember the animation on the previous slide, that's exactly where that hotspot was. This is probably one of the most common FRP failures, and it's just so unfortunate because it is completely preventable. Here we have a similar flange hub crack from over torque. However, from the outside only, we're looking at this, it's hard to know really just how bad it is. Now, what we might think is a minor surface crack, when we actually cross-section this flange, we saw that it almost went through the entire flange. And again, just completely preventable. A little sidebar topic here. A flange may look great on the outside. You can't see any different. But if you're not specifying them right, if you're not calling out the right ASTM standards, the right ASME standards, who knows what you'll get, honestly. You might have a lot of filler putty like there is on the flange on the left, maybe glass kind of shoved in there, in the flange in the middle there. You see there's actually no glass and outside the bolt holes there. Extremely weak flange, and that's aside from bolt torque issues. This is just a poorly made flange that is going to be very, very weak. The picture on the right here is showing how flanges should be built. So when flanges are built, you have what you call rings and risers. So the rings are laid down, just kind of donut rings to build the flange face thickness, and then they're alternated with risers that has the flange face thickness and then extends up the nozzle neck here. So you can see this kind of animation I'm putting in here of what's really being done to make this flange integral and strong, much stronger than the other two. If you buy the flanges on the left, flange failures are much harder to prevent. So we can go on and on. I'm not gonna do that, but just notice that this is exactly what the FEA predicts. So the mode of failure isn't hard to predict. We know how to prevent these failures, but we're not the ones torquing these up. So force installers to use torque wrenches, make them document their bolt sequence and torque ramp up in percentages of the final torque. Have them sign off on flanges. Make sure you know that these flanges are being installed correctly. So that's radial load. What other loads are we worried about on flanges and nozzles? Main other load for nozzle analysis is a bending moment, which is created from a lateral or shear load at the flange face. Again, this causes the same peel concern as with the outward load. So what happens from this moment on a nozzle if it's too high? Well, nozzles primarily fail either due to overload, poor installation, or inadequate reinforcement. All three need to be addressed. Now, it's important to point out that the installation that you see on the left doesn't seem like it should be correct, does it? It seems kind of flimsy. But I'm here to tell you, technically it can be okay if you only require RTP1 minimums for reinforcement pad design. If you don't like this, you have the ability to specify more, and that's what I'm here to tell you. Not all nozzles get repads. Some just have an attachment laminate. Now, most should have internal laminates, but we know that's not true in all cases. Sometimes you have a post-installed flange that you can't get on the inside, or you have an emergency where you just have to put a flange in, or you literally can't get on the inside, it's too small. And not all internal laminates are strong either, because mostly they're just corrosion barrier replacements. So note on the animation here, the peel you see, which is in red, which is from that bending moment, that tension load. We'll revisit this later when we're talking about trying to prevent the failures. But here are some examples of failures due to an excessive load on the nozzle. So what causes these moments that result in peel or delaminations? Well, sometimes it's connected piping. It could be dead weight, heavy unsupported equipment. You could have thermal expansion issues, but either way, if you overload that nozzle and bending, now you start to see that delamination and peeling at that bond line. Here's an example of a failure that's due to poor engineering, and it could be installation too. It's hard to know afterwards, but note that there's a U-bolt at the grating below. So if that pipe, this is a pipe, it's not a tank, but remember, it's all the same. So if that pipe wants to move, that U-bolt isn't letting it. So that's inducing that bending moment. So my eyes tell me that this seems to have been repaired at some point. Whether it has solved the issue or not, I can't tell you, but it doesn't seem to be currently leaking. More pictures of poor engineering where you have connected piping. Again, this is the header, but it's important to note that you're not going to be able to get on the inside of this header, especially after it's been installed. So internal laminates are not a problem. Rule of thumb, if you have off-color laminates, it's usually a good indicator that there are some problem areas, but it doesn't mean the problem is solved. It could just be a Band-Aid. But because there's no internal laminate, all you're gonna end up doing is throwing laminate on the outside to hope it fixes the problem, unless you actually do some engineering on the piping to make sure the reactions are minimized. So here's some examples of failures due to a lack of reinforcement and likely poor engineering, honestly. I'm here to say do it right the first time. When this is 50 foot in the air and it's extremely inaccessible, you need scaffolding or man baskets or whatever, the choice to repair becomes a lot harder. The picture on the right, you need to repair that, but picture on the left, you might say, okay, it's not actively leaking, so we're just gonna monitor it. But obviously there's something wrong there. But after it's installed is not the time to know that. Okay, so hopefully I've shown why nozzles can be susceptible to failures due to how they're installed. So that could be because of the gaps, the bigger gaps and more peel. It could be lack of reinforcement, it could be poor engineering. I've also shown that there are several different causes of these nozzle failures. It could be overloaded due to high load, lack of engineering detail. It could be over torqued. There could be a lack of repad for any additional loads beyond what RTP1 requires. Could be poor manufacturing of the flange. It could be poor installation of the nozzle. There's so many different aspects here, but all of these need to be satisfied in one way or another. Some are obviously easier to do than others, but from this point on, I want to discuss some safeguards that can be put in place to strengthen the nozzles without much additional consideration or cost. So what are some simple steps we can make, or I can recommend to strengthen nozzles that the owner or the engineer can make that won't break the bank? So consider this detail, which is straight out of ASME RTP1 for a flush nozzle installation. Interesting to note here, you don't see any putty, you don't see any gaps. So this looks very ideal. It looks really strong, but just keep in mind that there's a putty radius there. There are gaps at that cutout. On the left here, you can see shell reinforcement style A. So there's two styles of reinforcement permissible per RTP1. Style A is on the left, where you basically reinforce the shell. Think of more like a doubler if you're familiar with steel designs. On the right, we have a style B reinforcement where the overlay, the nozzle is attached with an overlay, and then the reinforcement comes on top of that, which has the benefit of kind of reinforcing the nozzle neck there. So try to keep in mind style A and style B. I'm going to use it a little bit in the upcoming slides. So same load as a previous example where we showed that peel was a concern. In this case, I'm showing the style A repad with, we're shown in green here. Very similar to a doubler plate in steel, but don't expect it to close the gap. I mean, it's literally just there to reinforce the shell. So while stress and deflection decrease by 59% for stress, deflection is 30% less than just having the overlay alone, we can see that there still is a peel concern. So peel hasn't really been addressed just with the style A repad. Okay, what about style B? Again, same load as a previous example. The green is the repad here where it extends up the nozzle neck. In our estimation, our experience, this is much preferred since there's the added benefit of strengthening the overlay running up the nozzle neck. You can see here when we animate it, the stress and deflection are way down. It's almost 500% less stress. Deflection is down almost 300%. Everything is stiffer, but you can see that peel is still not completely eliminated. We still have those hot spots at the peel points there. So everything is stiffer, but there's still that potential for rotation that we haven't eliminated. So in certain scenarios, the nozzle on the left is perfectly acceptable per RTP1 designs. It doesn't seem right, but I can tell you it is. If the shell is made a little bit over thick, and maybe the pressure is low, maybe it's a nozzle high up on the shell with low hydrostatic pressure, so it's thicker, the shell itself is thicker than it needs to be. So RTP1 says if the requirement is less than 0.129 inches, then it doesn't need repad. The nozzle on the right, you see with the style B repad, where it extends up the nozzle neck. So which nozzle do you feel more comfortable loading up? And honestly, when this is in the shop being fabricated, being manufactured, this is not that expensive to have them do. Also, to strengthen the attachment, you can add gussets. Sometimes they're required, 4-inch nozzles and below per RTP1, gussets are required. You can make them mandatory on any nozzle you want, really. But just note in looking at these pictures, they're not exactly robust. They can be thicker if you want, if the loads, if you do any evaluation on it and you decide you need what I call structural gussets instead of just a 3-mat 1/8-inch plate that's joined on. So you can definitely specify thicker gussets, but you can see just by logic how these would help prevent peel and rotation of that overlay that we've been having trouble with or that we've been examining in these previous animations. Does that mean all gussets are good? Well, not necessarily. You can't just throw in gussets. It doesn't ensure reliability. It's a stiffer neck for sure, but you can't overcome poor laminate quality, poor installation, high loads due to oversights in design or engineering. So FRP failures are almost always due to more than one flaw. FRP is really more forgiving than you might think. I know it's a brittle, non-ductile material, but it's more forgiving than you think. If only one flaw causes a major failure, it has to be a doozy. But this is why it's important to select good engineers, manufacturers, installers, inspect them, invest in engineering to understand the reaction loads. Just strengthening the nozzles alone, as I'm kind of explaining here, it's not going to fix everything if you don't address all of these aspects. So remember the peel concern. So we've established that adding external repads or gussets doesn't completely eliminate peel, right? So what's the best recommendation to solve this? So in my studies and experience, it's by adding an internal overlay. Internal overlays should be standard. They are in the RTP1 detail after all that I showed earlier. But per RTP1, it's basically a corrosion barrier replacement. It's basically to prevent permeation into the cut edges of the shell, of the flange, of the overlay. It's really just for a corrosion barrier replacement, protect everything from the fluid. There may be minor structure in there, but not a lot. So I say should be standard, of course, but I've seen a lot of equipment. Some of your equipment who is on this webinar here. Sometimes internal access isn't practical. There could be size, accessibility, could be an emergency repair. So internal layups, I am quite positive, are not on every single nozzle in your plants. So under that same load, just having that internal laminate on there, the stress and deflection reduction is pretty close to the style B repad, if you remember, but this is without a repad at all. It's just installation laminates. So the most important aspect that's in the box there is you don't see any of those hot spots where those peel concerns are. It's not red at all. So this nozzle installation with an internal layup effectively eliminates peel. Internal projections, you can see one on the picture on the left, definitely helps strengthen nozzles too. You can get a decent bond on the inside there, and you have a little bit more robust of a nozzle in there. But beyond anything else, hear me say internal laminates significantly reduce the stress risers that cause nozzle failures, particularly due to peel. So I know what you're asking, what does Maverick actually recommend? You want to know kind of what we would do, right? Some of you have seen our specs, some of you haven't. So in your specs, I would say for nozzles that are going to see significant load, if it's a spare nozzle, if it's a manway, maybe a little bit different approach, inspection port. But if it's got significant load potential, add internal overlays, and I would recommend some structural layers. I understand that could be an issue with reducing the ID of the nozzle, so you can't do it in every case, but definitely consider that. We recommend style B repads over style A all day long. And personally, we say, regardless of what RTP1 requires, put a 1/4 inch minimum reinforcement pad on there. That strengthens the nozzle. That gives you a little bit more room to work with, so you're not eating into design factors. So again, this will certainly help, but analysis is still required. That's not in place of all of this. You still need good manufacturing specs for quality. You still need good installation specs necessary for torque procedures and things like that. So we're going to segue now to the discussion about allowable nozzle loads. We hear this all the time. Why are my allowable nozzle loads so low? So you've probably heard this from a manufacturer. Sometimes they say 0, which is laughable, but let's see what RTP1 says. So in the mandatory section under sustained loads, it clearly says loads imposed by piping and ducting and other external imposed loads. They need to be considered. Now, way back in the sticky pages and non-mandatory appendix, note non-mandatory, we can see some fine print here where it says vessel nozzles should be joined to piping through a flexible connection or flexible piping system. So some of you watching have seen this before. You might see it on their bids, you might see it on the drawings, basically absolving themselves from any loads on nozzles because it should be 0 or basically 0, all from a non-mandatory appendix. So what does this mean? You just throw in expansion joints? Well, the irony about just throwing in expansion joints is they're not silver bullets, especially on these ones. If you look closely, you can see these have tie rods on the flanges. So if you have tie rods on an expansion joint that have tie rods that are maxed out, basically it cannot extend at all, well, all that load, if you have any kind of pressure or any outward load, goes right back to the nozzle. So that load is not 0. Theoretically, if it's supported or arranged correctly, the nozzle load can be very close to 0, but not with tie rods. And that's a big if. It goes back to the need for detailed and competent engineering. All right, so I've surely made some manufacturers mad. I think I'm going to get some emails from some salty manufacturers. So I'm going to spend a few slides here defending them. So we're going to look at an example here to back up actually why they're so conservative with their recommendations. So we're going to look at an example with a 14-foot tank. We're going to say the shell construction is all type 2, so just mat and woven roving. I didn't want to deal with unique properties. I just chose a shell thickness that I knew would work, and we'll look at a 6-inch nozzle with about a 1/4 inch repad. Note that I'm only going to look at this from nozzle loads alone at the start, no internal loadings. Also note that because it's FEA, it's not perfect, but I have to assume that it's a perfect attachment, i.e. no gap, no putty in this arrangement to be able to do this analysis. So why I'm not including an overlay is because, like I said, it's a perfect attachment. So that the overlay's attachment in my mind is to weld the connection. I don't want to consider it for any additional reinforcement. The reality is it does, but for my case, I'm going to say it doesn't. So with this perfect connection, we would have to assume that the internal laminates are there because this evaluation is not looking at peel at all. Remember, we looked at before, if you had an internal laminate, it effectively eliminates peel. So just from a radial load, just straight outward in that -y direction, this conceivably would have an allowable load of 1,400 pounds. So all of this is done just kind of experimentally to not exceed 1,500 PSI. You can see that the contours on the right, which is stress. So I just applied loads until I got it under 1,500 PSI and found that if this particular tank had 1,400 pounds on that nozzle, it would technically be okay, which is quite frankly a huge load. It's very big for a 6-inch nozzle. What if we only bent it in the longitudinal direction? So this is bending in the axial direction of the vessel, so around the X, rotating around the X axis there. This is about 525 foot-pounds for an allowable. Again, pretty good, but it's the only load. If we bend it in the circumferential direction around the Z axis, we're at 450 foot-pounds before it would become overstressed. So now what are you asking? Does that mean 6-inch nozzle allowables should be 1,400 pounds radially and 525, 450 foot-pounds? No. If we do all of these max loads together at the same time, logic tells you that it's additive, right? So all of these areas in red, all of these areas in purple are over the 1,500 allowable that we're trying to work under. So the stress is almost double the allowable stress, but right, it makes sense. We're adding loads. So we know we have to take into account the combination, the various combinations of loads that can happen. In this case, we're going to look at a case, these same max loads, but just add 5 psi of internal pressure. We know that the tank is probably supporting some internal loading. It could be hydrostatic, it could be a design internal pressure, so it makes sense that we should add some pressure to the tank itself. Now we see a lot more red. Just from this pressure alone, it added 900 psi of stress above the internal loadings. So the internal loadings on the vessel and how it was designed to satisfy those loads factor into the allowable nozzle loads as well. Remember, this tank may not have needed repad based on how they designed the tank shell. So I threw in a 1/4 inch repad, which might be more than RTP1 required, and based on those loads, were 2.5 times the allowable. So if we just have all the previous loads, we're not going to add pressure in this case, but technically we're okay. So we have 700 pounds and somewhere in the 225 to 250 foot-pounds of moment. Everything's acceptable. The loads are still pretty high, but remember there's no internal load. So if you add the 5 psi pressure back into it, you can add 900 psi to that, and now you're back to needing to reduce the loads again. Also note, if one of those loads is low, so say your longitudinal moment isn't 263, say it's 63, conceivably your circumferential moment can go from 225 to 300, for example. So there's kind of a massaging of loads depending on which one has the max direction. But remember, if you're asking the manufacturer for completely generic, universal, fully applicable loads for all possible situations, no matter any other considerations, they're going to be very conservative. So that's my defense of fabricators there. The manufacturer, they have to consider all these possible scenarios when you're asking for allowable loads, which would include, okay, shell diameter. If it's larger or smaller, that changes what the allowable loads would be. Same with shell construction. Our example was all contact molded type 2 hand layup. What if it's filament wound and is twice as strong in the hoop direction? It matters. What are the internal loadings? Is it internal pressure, external pressure, hydrostatic pressure? What's the repad thickness? This goes back to what does RTP1 minimum require versus what's actually put on there. The location in the shell, if you're just in the middle of the shell in a flexible region, you're going to get a certain allowable load. If you're near a bottom knuckle, a joint, a rib, the allowable load is going to be different. So the location matters, you know, in addition to diameter changes or construction sequences. And finally, combinations of loading. Like we just said, if you have a lower loading in one direction, conceivably it can be higher in the other, but they're not going to tell you that. They're going to tell you kind of the lowest of the low. So now you should be able to understand the tough position the manufacturers are put in when you're asking for allowable loads. There's no one size fits all approach. So in truth, you may not want to hear this, but every tank is pretty much a one-off. It's just not always obvious who's responsible for confirming this. And if it's not clear, if it's not clearly defined, then honestly, it's the owner's responsibility for clearing that up. So this slide here is kind of a throw-in slide. I want to give you some resources here just so you know that there are some options out there for estimating what a nozzle load could be. Say an engineer, they're not the manufacturer, they just have the tank geometry. They can use some of these references here to try to apply some loads to see what the stress would be to try to manage it without the help of a manufacturer. So there's a few different references out there. We prefer FEA. Honestly, if you know what you're doing, FEA can be faster than any of these other approaches. There's a lot of curves to be read in these other approaches. They're kind of difficult to follow and honestly kind of difficult to read. But note that there's assumptions that are still required. All except the FEA approach is based on isotropic materials. So it's all properties are the same in all directions, whereas we know FRP is anything but that. Film and wound construction affects stress distribution, magnitude, and ultimately what the allowable loads are. So you have to note, if you're using those approaches in the top 4 there, you have to make some assumptions. So recall our outline. We've discussed how FRP nozzles are installed, the loads and the other things that cause flange and nozzle failures, how to strengthen the attachments. We've talked about how to prevent failure. I explained why providing generic allowable loads is so difficult and therefore conservative, but that was just to show what loads can be put on the nozzles. So now the question is, how do we know what the actual loads are from the connected piping? Because if we're off on those, what's the point of knowing what the allowables are? For this, we need a final discussion on nozzle stiffnesses. Nozzles have some flexibility. They're basically like springs with finite stiffnesses. So even if we know what the allowable loads are, pipe stress, C's or K pipe, whatever you use for pipe stress, it's only calculating the loads based on your manual input of what that nozzle stiffness is. So how do we know those assumptions are even good? So contributing to every tank being a one-off, just like I was talking about a one-off for every single nozzle on the tank, it's not just the allowable nozzle loads. That changes based on geometry and construction factors that I previously mentioned, but the stiffness is in the same boat. The same variables apply: the shell diameter, the construction, the reinforcement, etc. The higher the stiffness you assume means it carries more load. The lower stiffness, alternatively, is more flexible. So what stiffness values are you assuming when calculating these reaction loads? If you've seen my previous webinar, you may have seen this, but I'm gonna restate it because I think it's very applicable for this discussion. So we're gonna show an example and kind of walk through these inputs here. So we're assuming a 6-inch diameter pipe. All we're considering here is dead weight loads and temperature. 2 anchor points at connections 1 and 2. For this first example, we'll assume that the connections are rigid, which is somewhere in the order of 10 to the 12 pound per inch or inch pound per degree, depending on what software you use for pipe stress. So if you assume these anchor connections are rigid, like I said, the stiffer it is, it carries more load. So the moment on that nozzle there is 3,000 foot-pounds. Remember, we were just talking about somewhere in the order of 500 alone is as much as you can apply. And with other loads, it's somewhere around 150 to 200 for this 6-inch nozzle. Well, what else happens? If you look at the pipe stress, which is all the analyst is doing, they don't really care about the moment so much. They think that's somebody else's job. Well, the pipe stress is 5,000 PSI. If you were operating somewhere around 1,500 to 2,500 PSI for allowable, you would say that that pipe is overstressed. It's bound up. It's got no flexibility. So an inexperienced analyst, they would look at this and they say, okay, well, you need expansion joints. You probably need to do large repads on the tank, but I'm not getting into that because I'm only the piping designer. If you throw an expansion joint in there, okay, well, that's extra hardware. There's an extra support that's required. Also, you need to figure out how to manage that thrust. Remember, is it tie rods? Is it no tie rods? You have to consider all of that. All because you assumed perfectly rigid. So let's say that connection 2 is rigid. In our example, we're going to say that's steel, it's bolted down, it's a pretty strong connection. But at that connection 1 at the tank, we're going to say it's a reasonable stiffness, somewhere in the 10 to the 4 magnitude. Don't use that. I'm just saying it's for an example, but in our experience, it's usually pretty close, definitely better than 10 to the 12. Like I said, the more flexible, the lower load it carries. So the previous example, they thought it was 3,000 foot-pounds. With a reasonable magnitude, we're dealing just less than 400 foot-pounds. Now we know, based on our previous discussion, that we're getting in the ballpark of manageable at that point. In this example, now all of a sudden we're not bound up. We have some flexibility. The max pipe stress is perfectly reasonable, acceptable, within the allowable. So remember, with the unrealistic assumption, they would have said, throw in an expansion joint, put some more repad, whatever, which would be costly and honestly introduce leak potential. expansion joints are maintenance items. They're certainly not cheap. So even if a manufacturer gave you loads, unrealistic stiffness assumptions would basically be impossible to manage. I'm saying this from experience. You'll bang your head against a wall trying to solve an unsolvable problem. Or you'll just decide to put in a ton of expansion joints or springs for a lot of cost, but to me, not a clear benefit. So speaking of stiffness, there are dangers of too much flexibility if they're in the wrong spots. So the FRP designer can do everything right. The nozzle on the left was not a problem, but if things are overlooked, it won't matter. It's not always the FRP's fault. I know, not what you're used to hearing. Everybody wants to blame FRP for failures. But in this case, just a rinky-dink steel angle was used for this anchor point on the right. The nozzle ended up carrying a huge load that it just couldn't handle. It wasn't designed for it. They couldn't have known because the anchor point flexed. When you're doing the analysis, you might assume that's rigid, right? Well, that's anything but rigid. So now what you thought was an acceptable stress in your T, in your nozzle, is now all of a sudden a catastrophic failure. So my final thoughts. The way FRP nozzles have to be installed is just what FRP construction forces you to do is a big contributor to why there can be issues. The owners or the engineers should establish minimum requirements for their nozzle reinforcements. So to reiterate, style B repads, 1/4 inch minimum repad regardless of calculated requirements. Internal joints if possible. Just be safer on nozzles with connected piping or heavy equipment. Don't expect large allowable loads if you're also expecting to have kind of generic loads that apply in all situations. I hope I've explained it well enough. There are just too many variables that go into predicting what the capacity, the nozzle capacity is. Now, if the nozzle stiffness isn't considered at all, the allowable loads are basically pointless. So nozzles that are modeled as too stiff, they'll make getting any allowable loads just completely fruitless. You'll put in a ton of expansion joints, you'll put in springs, again, for a lot of cost, but not a clear benefit. Finally, just take responsibility. Engineering and QC involvement will prevent many failures. Can't say it's going to prevent everything. It's not a perfect world, but it will prevent many failures. Make sure nozzles are taken care of. Control, honestly, what can be controlled? Engineering, specs, QA, QC, the whole shoot and match. Just control what can be controlled. If these are ignored, you can bet no one is paying too close of attention. We know this. We know from experience, and we're telling you this right now. The cost for front-end analysis, I know engineering always seems to be way too expensive, but the cost for front-end analysis is cheaper than expansion joints. It's cheaper than all the extra hardware that goes with that, especially if you're talking about stainless steel or Hastelloy. It's cheaper than installing new structures because you're throwing in expansion joints and you need more support points. Cheaper than spring cans for sure, and I don't like spring cans myself, so I never default to those. It's cheaper than repairs. It's cheaper than the downtime during your outages, and honestly, it's cheaper than lawsuits if you're dealing with failures or injuries or things like that. So front end work will prevent many failures. So with that, that's all I have. We've come to the Q&A portion, so hopefully you guys have some good questions. Can't promise I'll answer everything to your satisfaction. I'll be as honest and straightforward as I can. I may have to punt some and say I'll get back with you if I don't have a clear answer or if it takes a little bit more of a nuanced discussion. So Tom, bring on the questions.
All right, Darryl, we do have several good questions. Hopefully we can get 1 or 2 good answers out of them.
I'll do my best.
First question is, are there different types of gusset designs, and is there a preferred method, preferred type of gusset?
So typically you're looking at plate gussets. That's, I would say, the most common. And that's 4 plate gussets all the way around, evenly spaced. You can have conical gussets. That's also an option. Some like those. It tends to distribute the load a little bit better. You have no pinch points. Standard practice if you're not going to define anything else, we'll have the gussets stop about an inch shy of the flange face. So basically just connecting to the end of the nozzle there before it transitions to the flange face. So that in effect makes the flange kind of on its own. It kind of stands on its own. It has to handle all of those loads and transfer so it doesn't crack the hub, where we were showing that those kind of hub cracks earlier. There are options to extend gussets to the OD of the flange. There's different schools of thought on whether gussets should or shouldn't be attached to the back face of the flange. I can tell you it just gets a little bit problematic because of overlays extending into bolt holes, and there's a lot of obstruction. It creates noise if you're doing acoustic emission testing. It can be a problem if you're bolting up because it really stiffens up that connection. But honestly, that is a very strong connection. So there are different configurations. I can't say one is the end all be all, just like RTP1 has different style repads. We allow these repads because they both seem to work. So these different gusset arrangements are all acceptable.
Okay, that's one good answer.
Check it off the list.
Exactly. The second question came in and asked if there was a general rule of thumb for nozzle projection lengths to be used, or does each one individually matter?
So this can get a little tricky, especially when you're talking about replacement vessels, because per RTP1, it says 6 inches off of the OD. Well, if you know anything about FRP construction, OD changes with the wind, changes between manufacturers. Even if the manufacturer was going to make identical tanks, that OD may change. So you put 6 inches on whatever the OD ends up being, that may not fit up to your existing piping. You may need to replumb your piping, and we've seen that a fair amount. But generally speaking, we're talking about 6 inches minimum. If we're talking about manways, especially if they're higher pressure rated, like that one we see blew off, that was only about a 4-inch projection. Well, that's to the flange face, so it doesn't take into account the flange thickness. Let's say your flange is 2 inches thick, so now 6 inches went to 4 really quick, and now you have to get in there with an overlay, some repad. That's OD of shell, not OD of repad. So if you have inch thick repad, now you're down to 3 inches. So if there's the ability to increase the projection, especially on larger nozzles, I would say do so, especially for manways where it really doesn't matter unless you have some interference with platforms or gratings. Increase that projection to, I would say, 8 inches minimum.
Okay, thank you, Darryl. We've received several questions on the repad styles, type A, type B, which style, what are the pros and cons of each style, and why we would prefer style B. And kind of as a part to that, why RTP1 would allow both if one is a preferred method. So do you want to try to package all that together?
I'll do my best. Apparently I should have made that clear, or maybe I wasn't sufficiently clear about kind of what's what there. So, like I said, RTP1 does allow, I think if you ask most manufacturers, actually, they prefer style B. That's my experience in talking to manufacturers. So style A, again, we're talking about pure theory. What does it take to design your vessel for its loads, not other loads, not external loads, even though it says it in the mandatory section of 3A under sustained loads. It says external nozzle loads have to be considered. I can tell you it's not. It's not always done, I'll say. So these details are just generic. Okay, you cut a hole in your tank. How do we reinforce this opening? So that's when you get into the style A, which is very similar to steel, where they just use doubler plates. They say, okay, you took an 8-inch hole out, so we're going to make you put the effective 8-inch reinforcement back in to reinforce this opening, to remove any kind of stress concentrations. There's absolutely no consideration for increasing a nozzle's ability to handle external loads with the repad style. So that's why they're both allowed. But in practice, knowing reality and seeing too many issues, that's why we lean towards style B. So nobody can tell you style A is not right, but style B will get you off on a better path if you have connected piping or heavy valves, heavy equipment.
Fair enough. Good answer. Thank you, Darryl. Continuing with the flanges a little bit, and you talked a lot about torquing and proper bolt torque and stuff like that. So is there a generally accepted standard for how to calculate bolt torques? Or I know you know a lot about this and you've done a lot of work on this, but how
Yeah.
can the end user know what bolt torque should be used on a fiberglass flange?
Sure. That's a whole separate webinar in itself. And just know my hands are soft, they're pure. I don't hold a torque wrench. I'm not in charge of installing these. So I just talk purely in theory and purely from experience. But okay, so in RTP1, in non-mandatory appendix 12 for flange design, there are methods for calculating torque. But it's not a one size fits all. And that's primarily because of gasket selection. So FRP loves soft gaskets, elastomeric gaskets, but they're not correct in all services. Sometimes you need PTFE, which PTFE gaskets alone are extremely hard. Anybody who's tried to design flanges for just straight PTFE gaskets probably have a really difficult time. So you can use different types of envelope gaskets that still have the PTFE covering, but have an elastomeric inside, which reduces it. But all that to say, the seating stress requirements, the M values, they are all different depending on the gasket you select. So there's not, I can't just tell you, okay, it's a 4-inch flange, 25 foot-pounds. I know in RTP1, somebody will say that there's a non-mandatory appendix that has general flange torque values, but usually if you read fine print, it's all assuming elastomeric gaskets. So there are approaches out there. There are advancements in the industry, whether it's in RTP1, Section 10, or NM2 for FRP pressure piping. There are all subgroups in these different committees that are working on improving flange design, which will definitely consider gaskets. We're going to elaborate more on lap joint flanges. If anybody is familiar in the industry, lap joints are kind of an afterthought. There's not a clear calculation method for lap joint flanges. We're currently addressing that within our committee work. Standard rule of thumb right now is to say it should be the same thickness as a full face flange. However, a lot of times you use lap joint flanges because the gaskets get harder. So the lap joint has the benefit of having a smaller surface area that when you apply the torque, you get more pretension and you meet that seating stress. So how can you say what a full face flange would be if you can't satisfy the full face design for a hard gasket? So that's kind of the leap that you have to make between lap joint and full face flanges. So all this to kind of bring it back, the gaskets matter, the hardware type material matters, the actual loadings on the flange matter. It just matters that you pay attention to it. There are resources out there, and I would say get a min and max range and kind of start and torque to the lower end of that min range. And if you get a seal, great. If you don't, then you can increase it a little bit as long as you're not exceeding that max range.
I think you did a very good job of semi-explaining a very difficult subject, and that's why it's so confusing to most people out there.
Mm-hmm.
We have quite a few other questions, including one about dual laminate vessels and attachments that I'll probably ask you to take offline. There's one more that I think you can answer relatively quickly and easily, and you'll enjoy talking about. So you talked about internal joints on nozzles, and with the understanding that you do not typically classify the corrosion barrier laminate as a structural laminate, when do you consider balanced laminates? When do you consider putting additional structural joints on the internal?
Well, I would say, I mean, that's a really good question. And like I said, that goes with our recommendations that anytime you can get an internal structural overlay, do it. For a manway, quite frankly, there's no reason not to. Like I said, anything over 8.5 PSI of pressure technically needs an internal overlay. You don't want that just to be the corrosion barrier carrying that load, preventing that peel. there should be no obstructions with a manway. Maybe a little uncomfortable for, you know, you slipping into a manway, Tom, if you have a big bump on the bottom. But there's no obstruction. You're not fitting anything in there that you're worried about decreasing the ID. The only case I would say is if you have any kind of slurry or agitation, any kind of protrusion there, impingement area can wear a little bit sooner. So that's just something to pay attention to with internal inspections. The issue you get is when you are concerned about the ID shrinking. You know, generally speaking, you're going to put about, I think RTP1 requires 0.15 inches of internal laminate. So that's about 3 mat in a veil, regardless. So you're talking, you're reducing your internal diameter 0.3 inches right there. Well, if you add any structure to that, now you're coming down a lot. So if you only have a 3-inch nozzle, can you fit something through there if you have a dip tube or something like that? If the OD is, you know, 2.5 inches, 2 3/4 inches, it just doesn't work. So in those cases, that's when you get to the internally projecting nozzles, and where you know, do a different type of installation, so you get all the kind of overlay on the outside, and you're not obstructing the inside. So anytime it's possible, throw an internal, you know, a couple layers, woven mat, something like that. Throw a couple layers of structure so it's not all bearing on the corrosion barrier. And I'll talk briefly about the dual laminate question because I was thinking somebody might bring this up. And I'm guessing the question was something like, what do you do when peel is a concern with a dual laminate construction? Because you can't get an internal structural overlay on there. And to be completely candid, that's a very good question. We've talked about it at some of our last committee meetings where we could actually sit across the table from somebody and meet face to face. We had that exact discussion, and you get into unique solutions in doing that. You know, you have a physical limitation of the thermoplastic being physically welded, so you can't really expect to get an internal FRP overlay on there. So you're forced to do something maybe a little bit monolithic or integral, or come up with some other way. You know, if there's some other shear collar that you can put on, gussets certainly help to resist that peel. So I'm guessing that was what that question was about. I may reach out to that person individually, but I wanted to kind of elaborate a little bit on that too.
All right, Darryl, that suffices the majority of the questions. So I would say you've done a great job. Well done. Another great presentation.
Okay, so let me just take us out here. I want to plug our next webinar in March 2021. Put it on the schedule sometime in March. I don't know, maybe working with March 16th right now around the same time. We like to do these about mid-month. So this one will be by Jeff Eisenman, president of Maverick, founder. This one's surely to be interesting. Non-metallic piping in chemical processing. If you're not in chemical processing, don't not come just because you don't think you're in that industry. Everything will apply to you. We're talking about case histories here. Everybody loves some good case studies as long as it's somebody else's plant and not theirs. So this one is sure to be exciting, and that's going to be in March 2021. With that, that's all we have. I appreciate your attendance. Hopefully it was beneficial. Reach out. You have my contact information. Call or email if you want to discuss anything further. If you have any, you know, specific comments, questions, anything you don't think I touched on, I'm really happy to discuss this. So thanks again, and we'll see you next time.